So, good morning, everyone. This is lecture number 6, Digital MOS LSI Circuits E5 to 4, and today is September 24, 2020. In like past few lectures, we have studied following transistors like NMOS, PMOS transistor. Along with that, we have also discussed about CMOS technology. We also learn what is Moore's law. We also talked about CMOS inverter, how it has been implemented and using CMOS technology. Other than that, also like we also studied stick diagram and other layout issues and layout things. We also talked a bit about parasitics. So now the next chapter of this particular course is CMOS inverter, and thereafter we are going to go for the logic gates and their implementation, but that's the next chapter. That's the next chapter. Right now, what we are going to study is CMOS inverter. I'm following strictly one book, CMOS Inverter. I'm following the book Rabe, and for CMOS Inverter, I'm using the chapter number 5, CMOS Inverter. Okay, but before going to all these things, there are certain things we need to understand. Some people might have confusion, but most of the people who have studied with me, they must be knowing about following things like what we are doing is the large signal analysis. What do you mean by large signal? It says that the output of any circuit, it might be anything. If you are giving the input and if you are looking at output, if output reaches the VDD and ground, then that particular signal is a large signal. However, if you want to find out the small signal, you have to apply a signal small enough so that it may reach VDD ground, but not going beyond that. But if you are seeing the saturated one like this, then that particular input signal is a large signal. Note that it's a dynamics of circuit through which you can define it as a large signal or small signal, because sometimes the gain of the circuit is very high, so that very small input itself qualifies as small signal, and beyond some microvolt itself, it is large signal. Notably, in our circuit, when it's a digital circuits, where input is also going from actually 0 to VDD, and output is also I'm expecting 0 to VDD. It's a square wave. So in that case, we are dealing with the large signal. We don't deal with small signal, but there might be some place where we can use small signal as well if it is required. But this is the basic difference. Moreover, we also need rail-to-rail output. Rail-to-rail means the positive side here is VDD and negative side is ground. So I want the output which is going from ground to VDD fully. I don't want that the output is maybe a little bit higher than ground, maybe like this. I don't want that. I want the full scale value, but we are going to consider this one as positive rail, this one as negative rail. It's also logic 1 and logic 0. I want logic 0 to be as close to ground as possible, and same for logic 1. It has to be as close to VDD, and it's also positive rail. So output has to be rail to rail. So it's going from this rail to this rail. Okay. By the way, okay, third point is not valid for our thing, but yeah, you cannot go beyond this VDD and ground. That is already known fact to us. Okay, let's go to one more thing. So most important part is you need to know the transistor current equation. Many people must be knowing that, and I am not going into the derivation of transistor current equation. So there are various courses through which like this course is depend on. One is you should know this current equation. I don't mind whether you remember the derivation or not. It's not required so much, but it should be covered in device course where the derivation is there. In for BTech, it must be device electronics for integrated circuits. For MTech, it's called microelectronics and device modeling. So that must be the course where the derivation is given, and equation for the current. So drain current is equal to mu on Cox W by L VGS minus VTH times VDS minus VDS square by 2. By the way, this is the original equation governing all the different region of operation. Drawing the IV characteristic means output ID with respect to VDS. So if you draw that, then it looks like this one. And there is one parabolic line which is actually VGS minus VTH. So if your output is like, if you're going this side, it's known as saturation. If you are at this side, it's known as linear oblique triode region, any one of the region you can call it. It looks, it's actually, if you draw here, it's as good as linear line if you do it like this. So that's why we call it the linear mode of operation, and below that there is cutoff. We are not looking into that, but this is the way to find out. And if you draw other lines, it will look like this one. Okay, where VGS is increasing. So various values of VGS you can take. So VGS, if here it's 0.1, then this will be more than 0.1 and so on. So it's increasing. Notably, you can see here the the saturation curve. Actually, it's not a straight line. In ideal condition, it should be like this. However, it's not possible to have the straight line. It's going to be little bit with slope. So that slope is actually equal to 1 by R0. Some people are also calling it RDS, by the way. Both are synonym, by the way. It's known as channel length modulation resistance. Right. This is happening because of the short channel effect. So all these things maybe you will study in analog, or you might have studied in your previous courses. So these are the things. So the governing equation for all these different region of operation is as follows. If you don't consider the channel and modulation, however, if you are considering the channel and modulation, it's 1 by lambda VDS. Lambda is ratio of delta L to L. Delta L is extra overlap channel length, and L is the actual channel length you wanted to have. So channel length modulation constant, you can use it and you can find out. Moreover, if you want to see this, if you extend all these, base part of this is, it's going to be coinciding at one point. You can call this one as VA. Maybe all these theories will be taught in different courses. But the main thing is you should know how this transistor is governed. So this is the fundamental equation. You can write it down and you should use it mostly everywhere, wherever you want to understand how the transistor is behaving. Moreover, in all these different mode of operation, in saturation mode of operation, the current equation is like this. Because of this square, it's known as square law equation. But this is only valid for saturation region only. By the way, mu n is mobility, Cox is oxide capacitance, W is width of the transistor, oxide cap, mobility of n-type semiconductor, L is channel length, VGS gate to source voltage, and VTH is threshold voltage. Okay. And same way, like if you want to change it to PMOS, just you need to make it VSG with the mod, and this will become mu P. By the way, okay, I forgot to write divide by 2. In the case of saturation, it's divide by 2. Okay. So these are the equations. That is what I wrote it here. But different books are following different notation. Some books are following the notation of K. K with the subscript N signifies that it's N-type semiconductor, or it's NMOS, and if it is Kp prime, it's PMOS. So same equation, if you have seen my previous equation, which looks like this one. Right. So I'm just replacing the whole quantity with K. Notably, when you are going to study different course, and maybe people are trying to achieve high K material, high K gate dielectric, all these things they are trying. So when they are saying K is referring to this K, right? So this is the thing, and if you go deeper into that, it's mu n times Cox, where Cox is nothing but epsilon ox divided by Tox, right? So where Tox is the thickness of the oxide. Okay. So same way, like you can change the PMOS equation, where K will be replaced with Kp prime, VGS minus VTH, VDS minus VDS square by 2. So this is what you can write it down, right? And if you combine this W by L also, it becomes without prime, and we call it Kn. Okay. Now let's look at what are the requirements of our design when we are making any hardware or any digital circuits which are going to be made with the CMOS technology. We are very much concerned about the cost. Cost is associated with the area. If you are going more and more area, you have to pay more, right? So you have to make sure that you are making the compact design which has lower area. It has maybe, like, it's depending on sometimes complexity also. So you have to see that overall how much area is being taken, so that cost can be reduced. Other than that, I'm also interested in not only the transient behavior, which is dynamic, but I am also interested in the steady state behavior, that after settling, what is the behavior, whether it's going digital logic 1 or digital logic 0. Even if you want to make this circuit we all did digital. However, we have to understand that all this first order, second order dynamics are coming into picture, and they are going to introduce some of the kind of transient, or you can say that some kind of fluctuations at the output. And there might be the case that you are not achieving what you want. Maybe like what I want to say is as follows. You wanted to have the output like this, but you are seeing output like this, or maybe like this, or maybe like this. So there must be some offset. Even after settling, there must be some delay. There might be some, you can say, rise time. In other side, it becomes fall time. Thereafter, transient, then settling, and then at the end, it's a steady state of the static behavior. So all these things we want, and we want to understand what is going on. But the most important part is known as the energy efficiency. Energy efficiency is also sometimes known as figure of merit, or sometimes people call it FOM. This has certain things which are part of its equation, where you are not only talking about some of the required design requirements, but you are talking about few key requirements like energy and power. Along with that, maybe delay. I mean to say propagation delay, or all these things. So when it's energy time delay, power time delay, all these going to give you the figure of merit. We are talking about this thing because look, some guy might be making the circuit in 28 nanometer, and you are making in 180 nanometer. This 28 nanometer works at 1 volt. This is working at 1 volt means I mean to say that VDD. This one works at typically 1.8 volt. So power consumption will be definitely higher in 1.8 volt, right? But if you want to compare two technologies, you should not talk about only one particular parameter, but you have to look at the figure of merit, and that is also defined in different design. It's different thing, or you can say that we might be interested in energy efficiency. So energy has to be checked, how much energy is being consumed by particular design. Then you can say that okay, my design is good or bad compared to one with another technology. Definitely, if as you are going the down technology, it has always an advantage that you will achieve the better performance, whereas better performance are not possible at bigger technology. However, if you are just qualifying for your technique, sometimes technique works. So technique wise, if it is good techniques, maybe you can compare that technique with the older technology, and you can qualify whether that technique is good or bad on the basis of figure of merit or energy efficiency. So that's what generally we are doing, right? So these are the design requirements when you are starting with any design. Now let's talk about few more facts that we are making an inverter like this only. Rather than that, why this is the design? Like what I mean to say is, this is an inverter, but some places I need just a buffer. Means in that case, what I'm going to do, I'm going to keep two inverters back to back. I could have done something else than this one. I could have done this one, right? Reverse of this. But here there are two different circuits has two different outputs. One is inverter, one is buffer. If you must be remember how we have found out this one. So here, if we follow the same technique, what it says, if the input is for this circuit, if input is equal to VDD, output should be equal to VDD. Okay, I'm just saying that should be VDD. And if input is equal to 0, output should be equal to 0. But here some following things will happen. Let's assume that there is, I'm not going to do this. If there is an NMOS whose gate is connected to VDD and this particular terminal is connected to VDD. I'm doing this just to make sure that we understand that source and drain are interchangeable. For NMOS, VD will be greater than VS. So if this is connected to VDD, definitely source is connected to the lower potential than this one. Means this is qualifying as drain, by the way. Even though I don't draw the arrow over here, this is acting as a source. Let's assume that I'm connecting here a capacitor, just to understand that how it will behave. So if gate is connected to VDD, this switch turns on and this terminal is rising towards VDD. But note that before going to VDD, there is a point where it's VDD minus VTH. So as per the following equation and the characteristic, which is VGS minus VTH, and here ID versus VDS, if I'm going beyond VDD minus VTH, my transistor will be turned off. If I'm going beyond VDD minus VTH. So this source has to be at VDD minus VTH just to make sure that this is in turn on condition. So here you can say that how much you can try hard, but you can't achieve this source more than VDD minus VTH. It's impossible. You can get lower than this one, but not more than this one. So this clearly signifies that there is a drop of VTH over here. And whatever we are going to see here is VDD minus VTH. So at the best case, in the NMOS, if you are connecting this to VDD, you can transfer here VDD minus VTH. And similarly, if you try for PMOS, this is connected to 0, this is connected to 0. You can again think about it, what voltage you can get it here. It will be VTH. Otherwise, if you're going below that, again this transistor will be off. So what I conclude from these two things, if I am connecting 0 over here, then it's creating a problem. But if I connect here VDD, I can transfer the whole VDD over here. You can think about it maybe, and you'll find out that even if its VDD is going here, there is no drop first of all. And this transistor will not be going into the turn off condition. And same thing will occur over here when we make it in a reverse way. If this is 0, and if I want to transfer 0, then there is no. This is happening with the fact that it's following the current equation, right? So from here we can make two important conclusion. One says that NMOS can transfer logic 0 strongly, whereas transfer of logic 1 is not efficient, or there is some drop. Same thing, you can write it down here with the PMOS, where PMOS can transfer logic 1, or I can say that strong logic 1, and logic 0 is very poor. By considering this fact, if I draw this circuit, I know that when I'm giving input is equal to 0, output, so this becomes on, so output is equal to VDD, whereas when input equal to VDD, this is off, this is VDD, this is 0 volt, and output is equal to 0. However, if I change the location of the devices, means NMOS becomes PMOS and PMOS becomes NMOS. By the way, this is most of the time like people are asking the interview why this is strong logic 1 and strong logic 0. So this is an interview question. You should know that, right? So if input is equal to 0, then this particular transistor M2 becomes off, M1 becomes on, but output is not equal to 0, that's approximately equal to VTH. Whereas input is equal to VDD, then output is not equal to VDD, but there is some drop, and that is equal to VDD minus VTH. So although this is a buffer circuit, or you can also call it driver circuit, but whose output is not from rail to rail. It's not full swing, it's going from something called VTH to VDD minus VTH. Thankfully, I believe that VDD minus VTH and VTH will be qualifying as logic 0 and logic 1, depending on the noise margin available. So then there is no problem. But the conclusive remark is NMOS is a strong 0 transfer device, where PMOS is a strong 1 transfer device. And that is what we are doing by making this inverter with this kind of setup, where it's only an inverter, but when you want to make even logic gates or some other things, we'll make sure that all PMOS will be connected to VDD side, and all the NMOS will be connected to ground side. And we are going to call this particular network, where lots of PMOS will be there, as power up network. Look at this particular network. It's making the connection with upside. Upside is VDD. Whereas this NMOS is connecting with the downside, which is ground, or the power down device. So we are going to call PUN, and this one is PDN. But like in detail things we are going to talk in the next chapter, when we are going to add so many PMOS and NMOS devices just to make a big logic gate. So right now just we are going to deal with just one inverter, because inverter has lots of things to understand, and on the basis of inverters understanding you can go further with combinational logic, and later on going to the sequential, and of course you can take use of all these things to the design of memory and maybe processor. Many things you can design through here. But this was the conclusive remark, that we need to make a circuit where, if you remember the demarcation in the stick diagram, upside will be PMOS and downside is always NMOS, where all PMOSs are connected with the VDD. So the silver bullet says that till now you were here. Okay, this is for a moment it was happening. Okay, so CMOS technology has the biggest advantage is as follows, that it has a zero static power. If you look at that, the static power is zero, but in the case of NMOS, that was not possible. So that's why, like, to achieve static power consumption could form upper bound on the number of gates and other many other things were there, which becomes complicated with NMOS technology. Whereas in CMOS, because of the complementary devices, NMOS and PMOS, there is zero static power possibility, and this also gives us possibility to scale the technology. Scaling the technology means I'm talking about the Moore's law, which says that the current technology is, if it is 28, next will be 21, later on 14, 7, 1, and so on. Okay. Now, first I'll try to keep the things as with the intuition rather than going in the equation. So, if there is a CMOS inverter, if I want to draw the V out with respect to V in, note that most of the time, like even if you draw here or not, there will be always a load capacitance. If there is no load capacitance is given, there is one condition called self-loading. Self-loading means the capacitor offered by these transistors. We will talk about that later, but of course these capacitors will have overlap capacitor, and those will act over here as load. If those are not there, then there will be some loading. Loading will be considered. That might be CL. Now, depends on the fact that you are going to see your circuit on oscilloscope. So if this is your circuit, you might have function generator. So when you are connecting here from the function generator, actually in this particular circuit, it's going to see the 50 ohm load, because that is the setting you are making in this function generator as output utility, that it's 50 ohm. You can make 1 mega also, but the worst case condition is 50 ohm. This is a fact of the condition for BNC. So 50 ohm, I assume that from where I'm going to give my output, it's at 50 ohm, and it makes sure that wherever it goes, if it is 50 ohm, it can transfer, like as per the maximum power transfer theorem, it can transfer the voltage. If it is not there, this particular signal will be reduced. Now I'm saying this circuit will have, so this is acting as an input, whereas if you want to see the output, note that if output is not connected, then it's a self-loading condition. It will take the output impedance and output capacitance, output resistance as output or RL or CL. Whereas if you are connecting the oscilloscope, it is now that this oscilloscope is actually loading or acting as a load to your circuit. By the way, all the chassis of all these instruments are grounded. So if I'm seeing that this particular device is going to load me, if I want to find out how much load will be there, then you have to understand that what kind of probe you are using. It might be like 1x, 10x. Different probe conditions are there. So if let's assume that I am using the 10x. So in that, it's around 10 picofarad with 10 mega ohm of resistance is there. These are the numbers from the company who is making these probes, right? But these are the numbers they want to achieve. If you look at the available probes in our laboratory, IIT Mandi's laboratory, you will see it's 15 picofarad with something like 15 mega ohm or some kind of number which is near to these numbers. will be there. And if you go for 100x, it becomes 150, 150 pico, 150 mega, and so on. So generally, we consider that as a load. So if you are going to see this on an oscilloscope, you have to connect the value accordingly. If you are going at 1x, generally we take 1 picofarad because that's coming from there. Sometimes you know that the resistance is also there, but right now we are not going to consider resistor because we are more towards the value of CL, because we are going to work in a frequency domain where the capacitance is going to limit the bandwidth. So that's the main reason why digital circuits we are going to consider the load capacitance rather than considering load resistance. However, you can consider load resistance also, just to make sure that how the RC time constant or those things are affected. However, we are going to use load capacitance. So load capacitance, if it is there, it's good enough. Like you need to consider the oscilloscope's impedance along with the probe. Whereas if it is not there, it's a self-loaded condition. And then you have to see. Okay. So now let's assume that load capacitance is there with some value. So then how the output will look like. So let's start from here. If the input is equal to 0 volts. So if I am giving 0, I know that this transistor is become on, this transistor becomes off, and the Vout is connected to VDD. Note that PMOS is very good device in terms of transferring the logic 1. So logic 1 will be transferred, means will be fully transferred, no problem. Now let's consider the reverse condition where the input is VDD and output will be become 0, with the fact that digital logic 0 is strongly transferred by an NMOS, whereas PMOS is off, so it will be 0. If you draw this, it will be something like this. But in between something will happen. Let's assume that the resistance offered by this PMOS, resistance offered by PMOS is equal to resistance offered by NMOS. Means it acts as a following circuit. Under the condition that if I am giving input as exactly VDD by 2. If this is the case, both the transistors are on. Notably, in this condition, both the transistors are acting as saturation mode of operation, and the output will be exactly half. But this is happening when you have assumed that the resistance offered by PMOS is exactly same as resistance offered by NMOS. This is not the condition happening. We as an engineer have to create it. We will learn it when we are going to make the CMOS inverter. So if you connect all of them, it will look like this one. So during the transition, it's an undefined state. This might be, this is logic 1 and this is logic 0. By the way, we are going to call this one as VOH output at high side and VOL output at low side. We are going to call also this one as VIH because till the input, till the value of input, output stay as high voltage. We are going to define it as VIH. This one we are going to define it as VIL. In between VIH and VIL and VIH, I made a mistake to call this one as. Okay, this is correct, right? Right. So with this values between VIH and VIL, it's undefined. So this was with the intuition. You can see that this is going to happen and this is an inverter. And note that we are going to have the rail to rail output or the full swing going from 0 to VDD. If you replace both of them, the output does not look like this one. Okay. Okay, next, let's move to the next thing. So even though like this is a digital circuit, but you can't avoid RC circuit and understanding of control theory and other things, because whole dynamics, or you can say you are seeing some sort of fluctuations at the output when it's in the transient. All these things happening because of the RC time constants. So let's look at that. Let's assume that there is an RC circuit. This is a revisit for mostly everyone. Maybe you can use your notebook and you can draw this. Draw the transient response when applied input is square wave. So if the input is square wave like this, the output will look like this one. I believe people can understand that there is no output look like this one. This will not happen ever in this circuit. The reason is this is a first order system only. And fortunately, first order is only giving me the phase of 90 degree. So minus 90 degree. And because of that minus 90 degree, its phase margin is 90 plus 90 degree, and there is no fluctuations. If you're going with the, like if your phase margin is 45 degree, then the whole problem will occur. Okay. Now, find out the transfer function of the system. So transfer function is already known to us. It's 1 by CS plus R plus 1 by CS. That's going to make this 1 by 1 plus RCS. So there is only one pole in the system, which is at minus 1 by RC, right? In radian per second. If you want to make it hertz, you have to divide it to 2 pi also. Okay. Right. So there is no other zero, by the way, in this system. Now I want to draw the frequency response of this one. So I can draw the frequency response, means the Bode plot, 1 by 1 plus RCS. So the frequency, which is minus 1 by RC, note that we are making this Bode plot where we are making the mod of this transfer function. However, if you are going to draw at the negative side, same will be there, right? So it's a symmetric one, and we are assuming that it's a plus side. However, same frequency at the minus side, same will be there. Okay, and we are only making the system for the causal system rather than non-causal, so that's why we are taking care of just plus side. Okay, so this is already known to us. So this is in dB with respect to frequency. So the frequency response will like this with minus 20 dB per decade. Right? This is only one pole, so phase is equal to minus 10 inverse omega RC. Right? So you have to replace Laplace operator with j omega, and you will find out this one. So the phase is going from 0 to minus 90 degree, and that is what I have written here, because I thought that some of the people will not able to follow. That's why I draw this one. So going from 0 to 90 degree means if you are drawing the phase, it's going from 0 to 90 degree. So this is going from 0 to 90 degree phase, and at 1 by RC it's equal to minus 45 degree. Right. So in this case, there are no transient going here and there, as it is first order system, right? There is no second order, that's why this is happening, and it's going pretty fine. If it is second order, then this minus 90 degree will goes to minus 180 degree in the case of second order, and because of minus 180 degree the phase margin is 0 degree, and because of 0 degree there are fluctuations. As per the thumb rule, if your phase margin is 45 degree or less than 45 degree, you are going to observe some kind of fluctuations. These are the thumb rules. Okay, don't worry if you are not able to follow some of the things, but the main crux of the story is if it is first order, there are no transients. Okay, so if you understand that, let's go to the next thing. Like from here, what we can find out, if you are applying square wave, you know what is the RC delay. This is going to be useful to find out what is the propagation delay going from low to high and going from high to low using inverter, or maybe in the case of combinational logic. Notably, we want everything at steady state. We don't want anything in between. So this information will give me the information that, let's assume that this is the circuit, and I know that its bandwidth is 1 by 2 pi RC in hertz. So I know that if I am going to go beyond this particular number, V in is not equal to V out, right? So that's a bad part of this circuit. So, but this information is enough for me to know that this is the bandwidth. So I should not apply any input which is beyond the bandwidth. So this is the information I'm getting. If you are applying, what is going to happen? Let's say this bandwidth is 1 mega and I'm applying 100 mega of input. So then what is going to happen? Till the time this reaches, maybe let's assume that here it's 1 mega. So from it takes so much time to reach here, but before that the output has to change because input is changed. So your output will look like this one, something like this, right? So, and if you increase the timing, you will understand that the things are as good as you are seeing something 0, and that will be treated as logic 0 depending on your noise margin, high or low. So that's what we need to understand, that we have to restrict ourselves to the given time constant. Find out the transfer function means nature of the circuit. If it is first order, things are pretty fine. If it is second order or third order, things becoming worse and worse, because even if you are applying for a given frequency, you are going to see some sort of fluctuations. But as long as it's getting settled before the clock change, it's okay, fine for us. Okay, and we need to understand where the poles and zeros and all this condition, and we also need to know the bandwidth. So these are the informations we are getting from this circuit. Okay, so that's all for today. Maybe we'll talk more tomorrow. Tomorrow morning, 10 o'clock, we will have the lecture. So thank you very much. In case of any doubt which I can answer.